So you might remember early in the semester I mentioned that there are going to be some upgrades to this room over spring break, primarily dealing with the stuff that's up here. And while this old-fashioned kind of desk area might look, it does look old, that hasn't changed, but my interface with the projectors and stuff has changed. These monitors are new. But one thing that's kind of weird is that they upgraded some of the equipment that goes underneath this desk here. And depending upon how far away you are, you might hear a loud fan noise. That fan is coming from here. It appears they have not properly ventilated this underneath the desk here. So I've put in a request with technical support for UNL to see if they can fix that. But at least for me, since I'm standing right next to it, it's quite annoying to have this loud fan. And so hopefully that will be fixed. Now also, since we last met, I think the last time that we met actually, some students indicated there were some problems with RStudio on these computers. The computers had RStudio installed on them, but they didn't have R installed. So that meant RStudio was worthless because RStudio requires an installation of R. So they have now installed R on these computers. Oddly, they chose to install a 1.5-year old version of R, but I did play around with it. It seems to be okay. But RStudio, though, is a 3-year-old version. And so when you open up RStudio, you'll notice some messages that pop up regarding how old it is. If you cancel through those messages, at least when I tried it on these computers, everything seemed to work fine except for plots. In the end, it's not a big deal. The plots open up in separate windows, similar to in my videos or when I do stuff here in class, how plots open up in a different window. The same thing will happen to you in RStudio. But just so that you're aware that that will happen, I just wanted to let you know. I do recommend that if you didn't do this before class, maybe after class, make sure you can log on to these computers. You can do a little bit of R programming in RStudio or whatever. You could just use regular R as well, just to make sure that you're comfortable with it, okay? And then if you did have questions, I'll be here for you. Okay. So for today, you needed to examine the first subsection of 2 subsections on forecasting. Now, that's one of the main purposes of of doing time series analysis is to forecast the future. And what that basically means is this, that we want to know what x sub n plus m is, meaning that we've observed n values in our time series. And we want to go m as in Mary, time points into the future in terms of our predicted value, our forecasts. And all that this forecast is actually a conditional expectation. And hopefully this makes some sense, that I'm going to forecast the future with what I expect x sub n plus m to be on average, given my past information I have available to me. We denote this expected value symbolically like this. So we have an x. We put a tilde on it to let us know, okay, we're dealing with a forecast. What do we want to forecast? We want to forecast the n plus m value. And what information do we have? We have information up to time point n. So if I had something like this, let's say x tilde 105, and then a 100 in the subscript, what that means is that I want to forecast 5 time points into the future, given I have information on 100 time points to begin with. Okay? Now, make sure that you can go through the derivation relative to these ARIMA models that we have. Make sure you can go through the derivation of how to find a forecasted value. Also, the way that we're primarily going to actually do the computation is using the predict function in R. It makes it fairly easy. In this section, we also saw a number of different plots. Whenever you do a time series analysis, typically you do some kind of plot associated with it. So it's really cool to be able to see where those forecasted values are on that corresponding plot of the data versus time. Now, in our next set of notes that you look at, the second part of forecasting, we are going to look at confidence intervals for x of n plus m. Because after all, we're coming up with an estimate. Once we put in the estimated parameter values for this x tilde, we get an estimate of it, and we know that it's not perfect, but we would like to be able to say, let's say with 95% confidence, that the true future value is somewhere between two different numbers. So we want a confidence interval for. We'll learn how to get this confidence interval in the next set of notes. Again, this forecasting stuff is not on test number 1. Are there any questions? Okay. So since we last met, all of you should receive your project number 2 back. The projects were very good. Thank you very much for nicely formatting the projects. It makes it easier for me to grade. And also, of course, once you're outside of this class, you should always strive to have nicely formatted stuff too in terms of reports that you might be generating for a data analysis. Average score was 51.6 out of 53 points. Very small standard deviation with this. Okay, so let's talk about just a few things relative to what was in the answer key. And again, please make sure you look at the full answer key. I know, again, all of you did well, but make sure you do look through all the answer key itself, even if you got the corresponding problem right, because I might have approached it in a different manner. And we want to look at what ends up being 3C here. I'm sorry, 1C, where we needed to examine some estimated ACF, estimated PACF plots for the earthquakes data and come up with potential model ideas. And so here's those corresponding plots. And so we see that we have a significant value here, a significant value there, although it is somewhat borderline still. Okay? So we need to figure out what a value of P should be, what a value of Q should be. And so one potential way to look at this is as follows. Excuse me. Perhaps what's happening here is I'm having a tailing off to 0 after, let's say, maybe lag 1, or starting at lag 1. We also have kind of a tailing off to 0 there as well. Now, this isn't perfect. This isn't as perfect as what we saw, for example, in subsection 6 of our notes. But that would be one potential interpretation of this. And if I can say that the tailing off starts after lag 1, then that tells me P equal 1, Q equal 1, because I have it in both plots. Now, that's one possible interpretation. It is definitely not a perfect one. And so that's what I had here. Another possible interpretation is that the PACF plot cuts off to 0 after lag 1. Let me do a little bit of erasing. Okay, so again, we have this somewhat borderline significant value there, and then you can say, well, essentially after that, well, everything's not significantly different from 0. That doesn't mean it is 0, but if I were to interpret it relative to, let's say, an AR1 model, I would need it to be 0. Then this also means then if I had an AR1 model, that I have a tailing off that starts at essentially lag 1. So it says, okay, I don't need any moving average terms. And so in this case, P equal 1, Q equals 0. I think those are the two most, most likely possible models here. Now, one or two groups said, what was it? Perhaps, let's see, Q equal 9. Because it got a little bit of a borderline right there. Okay? But the problem with talking about that is that you might be worrying, well, what about everything in between? That's really jumping far ahead. And so that's why I don't think that kind of a model will be definitely not the most obvious. It will be really hard to justify. Now, looking at these kinds of plots is a main tool that we'll use to come up with an initial idea. And typically what one will do is maybe be somewhat conservative in what they choose for what P and Q are. Meaning don't jump to P equal 20 or something like that. Then once we choose one of those models and fit it to the data, then we'll have actually some other tools that we'll be able to use to help us refine our choice. So that is coming up. So don't think that, okay, this is the only way that we can do it. There's other things that we're going to be doing to try to figure out what would be the best model for our data. Sorry if it seems like maybe I'm talking louder than normal. It is really distracting having this loud fan right next to me here. And maybe I'm talking louder because of it. And so I want to show you basically a picture I took of a piece of paper that I wrote on our last Thursday class. Because there were at least two groups, maybe three groups that were here in class on Thursday, and they were having questions about that tailing off or cutting off to 0 and stuff like that. And I ended up drawing some plots here. You can think of these as ACF or PACF plots for what are common patterns that you see for tailing off. So in this first plot here, so maybe this is the ACF, okay? And we have lag on the x-axis, and we can see that we have this tailing off that's occurring because the ACF estimated autocorrelation values are getting closer and closer to 0. Now notice that some of them are significantly different from 0. That's completely fine. It's part of that tailing off pattern that's occurring, that the ACF values are getting closer and closer to 0. Now, that's one common pattern that you would see. Another common pattern then is that when we have this alternating tailing off to 0. Some are positive, some are negative. Same concept. We're getting closer and closer to 0. And then the third one is when you see like a sine or cosine kind of wave pattern with it. So this is very similar to what we had with the earthquake data. Okay? Those are the three patterns that you're going to see for tailing off. Now, there may be times where you'd be thinking, okay, where does that tailing off start? Does it start at lag 1 or does it maybe start after lag 1? And that's always a problem. Okay? And that's why we often have multiple models that seem to make sense, at least initially, based upon an ACF and a PACF. Now, if you have not already, in subsection 6 of my notes, there was a program, I think it was called ARMA Sample, that's set up for you to try a bunch of different possible models. And my purpose of putting that together was for you to actually try different values of phi1, phi2, phi3, or however many phis you have. Similarly, for different values of theta 1, theta 2, however many values of theta that you have, so that you could simulate some data. You can choose your sample size, simulate your data, and then look at the corresponding patterns that end up occurring with these plots. If you haven't done that already, that will be something very, very good to do, so you get more comfortable interpreting these plots. Are there any questions? Okay, so on number 2, go there. The purpose here was so that you could see the effect of sample size. And you might imagine that the larger your sample size is, the more these estimated ACFs, these estimated PACFs will look like what they, let's say, should in terms of like the true ACF, the true PACF. And you could see for a sample size of 25, kind of similar to what we had with earthquakes data, there was some resemblance of what we would expect, but then again, there was definitely some deviation from what we would expect too. And you can see how it can make it difficult when you have the smaller sample sizes. And so hopefully you notice that the phi1 and the theta 1 that I chose for this particular problem were exactly the same as what was estimated in number 1. I did that on purpose. So that helps you understand what we were seeing in that estimated ACF and PACF for number 1. Again, it helps you see that, okay, maybe an ARMA 1-1 model truly is the model, but it can be difficult to make that judgment based upon, I think we had a sample size of 24 for the earthquakes data. Now, where was I? Okay, I guess I did talk about everything with regards to 2C that I wanted to. One last thing with the project. So a number of you, when you're writing your functions, I think there was 2 functions you needed to write for this project, you use the function return in your last line of code for the function. That is not needed. R returns always what's in your last line of an R function. So it's not needed at all. One reason why I wanted to bring this up is that, especially once you get outside of this class, maybe you're working with some other people on some R stuff, or I don't know, you have to do something in R where somebody's going to see your code. If they see you use the return function, they will think that, how should I say, that you're old-fashioned. That perhaps you don't know your R as well as you should. I don't mean that in a negative way, okay? But it's something good for you to know that return is not needed. When I do see people use return outside of this class for something like research, it doesn't happen often, but I do. I start even questioning, okay, do they know everything about R that they should, if they're actually using return? Because return hasn't been something in R for a very, very, very long time. So just a small comment. Are there any questions with regards to the project? Okay, let's move on and talk about project number 3 then. This is due Thursday, April 4th at 8 p.m. Similar format as before. Now, this is, I think, 9 days away. Is it? Let me make sure I got that right. Sorry. Oddly, despite how many times I look at this schedule, I must have got it wrong. Because I had project number 3 discussion for next week. Okay. Now, I do believe that on the discussion board, when I handed back project number 2, I did mention project number 3. Is that correct? Or didn't I? Let's check. I apologize. Unfortunately, I am reaching the point where I have a lot, perhaps even too much for a person to do. Okay. I did have that there, so that's good. Now we can, even though on the schedule webpage I had it indicated the discussion on the wrong date, we can talk about it. I understand you're not going to be interested in starting the project before test number 1 coming up, because after all, the stuff that is on this project will not be on test number 1. But I'm sure about Thursday at noon, when you've recovered from the test, you will immediately want to start this project. So to help you out, let's talk about it. Seriously, it doesn't hurt to start the project before our next Tuesday class, even though it's not due to April 4th. Okay. Now, this particular project is smaller than ones that we've had in the past. It's worth, I think, about 38 points. And it just focuses on forecasting. I did this on purpose because, again, forecasting is one of the most important topics for time series analysis. And so I thought it would be good to have one project just focus on forecasting itself. Let's take a look at it here. The stuff that's highlighted in yellow is the stuff that you have enough background to start. So problem number 1 deals with the earthquakes data once again. And what you're going to do is use one of those models that, at least initially, we think might be a potential model for this data, an AR1 model. And part A here, simply estimate the model. So I guess this is actually from the estimation section, this one little part here. But part B says, okay, now let's compute the forecasts for the first 3 time points into the future. Compute it using the predict function. Okay, so you estimate the model in A. Now you do the forecast using predict in part B. Just so that you get used to the notation, please make sure that you do state the correct notation with these forecasts. So this x tilde sub 25 with the superscript 24 means that m equal 1 value, the first time point into the future. So don't just give me the results from predict, actually state using the correct notation x tilde sub 25 super 24 is equal to whatever it is. Then part C. I want you to compute these forecasts again. But now I want you to program in what those corresponding expressions are for these forecasts. Program them in. So it's going to be dependent upon, for example, phi hat 1. Program it in yourself and do the computation again. Now, in the forecast notes, you will see what those values are in a symbolic format. So I've already done essentially the derivation for you. You need to be able to now apply that derivation here to actually program it into R. Part F, plot the observed data, plot the forecasts. We will talk about the other parts next Tuesday. Then on number 3, for an ARMA 2.1 model, actually do the derivation for the first 2 time points into the future for the forecast. Okay. In my notes, I believe I have 3 different derivations in there. So that obviously gives you some experience with seeing that. Now I want you to do one that's not in the notes. Okay. So that's project number 3. Okay, any questions? Okay, now we're going to spend the rest of the time period discussing the tests. We're going to first talk a little bit about what I did, what we discussed last time in terms of the test format, just to remind you, because it is a different format for many of you. Then we'll talk some more specifics about the tests, and then we'll review the corresponding material. Okay. So again, the test is a closed book, closed note, closed video format. So you cannot use my notes, you cannot use the book, you cannot use any of my videos online. Obviously, too, you cannot talk to your classmates here in class. But what you can use is any of my R programs that are online. So during the tests, you can download them. And what you probably will end up doing is you're going to download a particular program. You're going to copy and paste some code into, from that program, put it into your own program that you're typing up for the tests, modify that segment of code for your own needs, and then run it. Then you'll get an answer then that you can use for the test. Also remember there is a PDF on my website as well that has important equations that we've talked about. And you can use the R help that's within R Studio as well during the tests. Note that this does not mean you can, let's say, Google answers during the tests. So the tests, I'll be in this classroom probably as early as about I usually get here about 8:10 or 8:15 in the mornings. I will make the test available on my website at 9 a.m. and you'll have till 10:45 to complete it. Now I had hoped to give you a little bit more time, like to 10:50 or something like that. As many of you know, the Department of Statistics is interviewing for a new department chair this week. And we happen to have something that all faculty are supposed to be at 11 a.m. It is in Hardin Hall, up on the 9th floor. So because of that, I need to leave this room by 10:50. So it'll probably take me about 10 minutes to get there. In the end, I don't feel as though it's a big deal that maybe you have a little bit less time than I had hoped for the tests. You're still getting an extra half hour for the tests. And the test is made, again, to be an hour and 15 minutes. So ideally, please turn in the test by 10:45, but I do need to leave the room by 10:50. So if you're still working on the test at 10:50, that's not good. You need to email it to me before that. Okay? The test itself will be in a Word document. Just put all your answers in that Word document. Most students have a laptop. If you do have a laptop, I recommend that you bring it to class. This is especially important this time because, as I mentioned, these computers are not exactly like I would like them to be set up right now. And my big fear is that, let's say UNL's computer support, ITS, they got my email today and they say, okay, well, we need to make further changes to the computer. They make the changes, and then when I get here on Thursday morning, I find out, some of the changes that they made totally screwed up the computer. That's a fear. Maybe I'm just too much of a cautious person, but I do recommend that you bring a laptop if you have one available to you. I expect everything will be fine, but given that we're now just 2 days before the tests, I am a little bit concerned that maybe something might go wrong. So be prepared. Now, of course, with the tests, you need to study for it. It should be obvious. But I want you to make sure that you're not too over-reliant on the information that is going to be available to you on the test, such as my R programs. Make sure you do study for it. I strongly recommend that you are familiar with what my programs are. I know that sometimes the way that students approach my class is they'll just copy and paste code from my notes and not really look at my programs too much. But obviously with this kind of a testing format, it is definitely helpful to know what's inside my programs. So if you haven't run my programs, run them before the tests. Look at what information is available in there. You don't want to be in a situation where I ask you to estimate a model, an ARIMA model, and you're wondering, okay, well, what's that code? I'm not totally for sure. I'm going to download one of Chris's programs and look. And if you end up spending 20 to 30 minutes looking through the programs to find out where I've used the ARIMA function and how I've used the ARIMA function, that's way too long. You are not going to be able to finish the tests. So you need to have some familiarity of what's in these programs. And this then gets into the whole idea of you need to have some kind of speed in actually being able to complete these problems. If you're constantly always having to look in my programs or look at even the equations sheet to complete the tests, you have not studied enough. So please, in your final preparations for the test, have that in mind. The speed that's needed to complete some of these problems. So in terms of the problems, the problem types. If you've taken a test from me before, it's essentially the same format. But I do know that some of you have not taken a test from me in a previous class before, so let's talk about it. Most of the problems are going to be of the following format. There will be multiple parts. So let's say problem number 1 will have maybe parts A, B, C, D, and E, where these parts are somewhat interconnected in some way. Very often what will happen is I will give you a data set as the introduction to a particular problem. And then part A, maybe you have to actually fit in a ARIMA model. Or let's say actually part A, you estimate an ACF and a PACF. Part B, you suggest what would be potential models based upon what you see for the estimated ACF and PACF. Part C, you estimate one of those models and actually formally state the model with using the correct notation. Part D, maybe you might do some interpretation. That's what I mean by a multiple part kind of problem. Another type of these problems is maybe I ask you to derive a particular quantity. So for example, maybe I ask you to write a particular ARIMA model as an infinite order moving average, and then follow it up with, given that information now, what is the ACF? Now, my tests typically and this is the case here, my tests typically end with one problem that is a short answer set of parts, where these parts are not interconnected in any way. And for this particular test, this problem only has two parts to it. Here are examples of what I mean by these short answer kinds of questions. This is actually from previous tests that I've given in time series. What is differencing? What is its purpose? So, what would you say here? Does anyone want to venture an answer? What is differencing? I mean, I'm hoping it's an easy question. Yeah. So you had to say that in a sentence. Okay? Short answer. Now, of course, well, what's its purpose? Why do we ever even think about doing differencing? Well, not to remove it. to make something that's non-stationary in the mean, make it stationary. And I would look for the word mean, because that is a key word there. Because there's different ways to have non-stationarity, and I would look for the mean. If the mean wasn't there, you probably lose a small amount of points. Differencing doesn't help you with respect to like non-stationarity in the variance. Okay, so that's an example short answer question. Here's another one that's kind of related that I've used in the past. Show why first differencing works to remove non-stationarity of the mean. Problems that you might have. Use this linear trend model in your answer. Now, in the integrated subsection of the notes, we did exactly this. We used this particular model to show that what happens when you have, let's say, xt minus 1, what happens? T disappears. Okay? That's why it works. That's why it removes the non-stationarity in the mean problems. So one will need to say this in one or two sentences. Any questions? Now, with the tests, you do need to show your work for any kind of computation that you make, for any kind of derivation that you get. You can't just, start with one line for the derivation and then say magically, I got the right answer in the second line. You do need to show your work. And if the shown your work is not there, that I will take off points, even if you get the correct final answer. And the reason why, and I think I mentioned this last time, is because partial credit will be available. So let's say that you needed to estimate an ARIMA model, and you accidentally got the ordering of P and Q incorrect. So instead of estimating what would be, let's say, an ARIMA 100 model, you accidentally estimated an ARIMA 001 model. Okay? And then you stated the model. And so, by showing your work in this particular case, you would show me your R code and our output, just like what we would have in the project. And I can see what you did then. I think, oh, okay, you just misplaced the P and Q. Okay, I'll take off a few points. Rather than if you didn't have that at all and stated in a moving average 1 model, it makes me think, okay, there's something else that's going on wrong here. And I would take off more points. That's maybe not the best example, but hopefully you get the idea. Show your work and why it's important. Also, what I mentioned last time is with regards to equations. There will be equations that you're going to need to write out on the test. I understand that not everyone is as comfortable using, let's say, Word's equation editor as I am, or using symbols in Word. And so because of that, it's okay to use a text-based equivalent to some kind of mathematical symbol, such as MUHAT for mu hat, or phi_1 for phi1. I just take phi1 itself too, or PHI1 would work. But do note that, if like something's estimated, you do need to make sure you say hat with it. Phi1 is different from phi hat 1. I need to make sure that you understand the difference there. One's a statistic, one's a parameter. To help you out, I will often give you the symbols that you may need for a particular problem in the problem description. So look for that, and then you can just copy and paste it. And something else I wanted to mention, because sometimes I find students who do not know this. So quick ways to be able to use mathematical symbols in Word is to set up a shortcut set of keystrokes to generate them. So for example, if I wanted to, let's say just type in quickly and try to do it quickly. Oh, why isn't it working now? Of course it's not going to work when I'm trying to demonstrate this right now. Oh. When I went through my notes yesterday to prepare for class, I had absolutely no problems. That. Well, something's not working properly on my computer, but what I will tell you is this. Let's say that you wanted to insert the Greek letter tau. One way to do it is always go up to Insert, Symbol, More Symbols, find tau in the symbol font, hit Insert, and there you go. That will be inserted. Another way to do it is to create what's called a shortcut key. Oh, okay, it is right. Okay, if I move my mouse here where it says press new shortcut key, and if I were to click, or if I were to select Alt-T, that will set up that set of keystrokes to automatically insert the Greek letter tau, so that when I would come over to my keyboard and type simultaneously Alt-T, I know it's not working here, but trust me, it's worked every other time that I've ever done it. If I were to hit Alt-T, it will actually insert the Greek letter tau automatically. And so that's how you can type quickly with mathematical symbols. Sorry that it didn't work here. Okay, are there any questions so far? Okay, next let's do a test review of the material. Again, the test only goes up to subsection 9 of section 3. It does not include the forecasting. I gave you some hints last time about how I went and how I prepared the test by going through all the quiz questions that we've had, by going through all the projects that we've had, writing down the main topics from what I saw from those questions and parts of projects, and then I use that to come up with ideas for questions on the tests. So that shows you what I think is important. If I think it's important, you should obviously study for it. Here's another example of what I think is important in these sections. So we essentially began in section 2. What is time series data? Well, we observe some information over time. We get x1, we get x2, all the way to, let's say, x sub n. We observe, let's say, n different time points. Note that we are not as formal with some of our notation here as we might be, let's say, in a mathematical statistics course. So we use a lowercase x to mean both a random variable and a possible observed value. In the context of what we do, it should be hopefully obvious. Do I mean a random variable or do I mean an observed value? This is standard in time series analysis in most places. And the key is with this time series, x1 through xn, we want to understand the dependence that exists in the data. Because if we understand the dependence, then we can then project what will happen in the future with that kind of dependence. In other words, we will be able to forecast. That's why it's so important for us to understand the dependence in the data. How do we understand the dependence? Well, we look at something called an autocovariance. We look at something called an autocorrelation. This autocovariance, autocorrelation is very, very, very similar to the covariance and correlation that you typically, all of you have seen in another class. The word auto comes about is that instead of, let's say, looking at the dependence between x and y, we are looking at the dependence between multiple x values. In other words, just different values of our time series. So that's where auto, same variable. And in section 2, we derived what this autocovariance, what this autocorrelation was for simple models. We looked at plots of x of t versus t, and we looked at those plots and we looked at, okay, I would expect that plot to have a positive autocorrelation, or I expect that time series to have a positive autocorrelation based upon what I see. I expect it to have a negative autocorrelation based upon what I see. Make sure you understand what we're looking for in those plots and why we look at that to make that kind of a judgment. And the purpose with doing this was to give you an intuitive feel for what dependence looks like over time. We saw how to estimate the autocorrelation and autocovariance. We have that nice ACF function that gives us the numerical values. It gives us plots of the data, and it gives us information to allow us to do a hypothesis test concerning the true autocorrelations. In other words, then we can make inferences regarding these values. We also talked about stationarity, what it means. And we typically focus more, though, on weak stationarity. And that basically looks at what we could say is the first 2 moments. We wanted to see if the mean is dependent, or I should say, the mean changes over time. We want to see if the variance, the autocovariance, equivalent to autocorrelation, if that is different over time as well. And, why do we want to do this? Well, because if we do have these differences, that might causes problems to try to now take the dependence that we see in our data and to forecast the future, because maybe in the future that dependence changes as well. And if you don't know how it changes, well, your forecasts are not probably going to be very good. So that's why it's important for us to have a weekly stationary data or time series. Then once we can say that we can work with weak stationarity, then we can transform our notation for, let's say, like an autocorrelation. Instead of being dependent upon two different time points, now we only have to look at the lag, which is the difference between the time points. We also introduced what was called the general concept of a linear process. So what that is that you can write x of t as a function of mu and some white noise, a linear combination of white noise values. If you can do this if you have a stationary time series, then that leads to a nice simplification to what the autocovariance function will be. You make sure you're comfortable with working with this expression for the autocovariance function. Excuse me. Oh, that wasn't good. So then we get to what is differencing, what is its purpose? Well, hopefully you remember what we talked about 5 minutes ago. Then we introduced some of this weirdest statistics notation out there, backshift notation. That's what these B's are. Make sure you're comfortable working with the B's. So if I have, in the simplest case here, B times x of t, that is x of t minus 1. Okay? Now, we can have non-stationarity with respect to like the variance. How can we take care of it? You can sort of take care of it by using some kind of transformation of our x of t. Like most commonly used one is the log transformation. We also discussed then, well, how can we simulate data through a for loop? And the reason why that's important, even beyond our coding, because of course then we have a function R that automatically essentially does it for us. But the reason why that's important is that because it allows you to understand better what our time series models are representing. So if I can have, let's say, a value, my most recent value, if I want to find what the current value is, well, I can just use this expression, and you can keep on doing that in a for looping structure. Then section 3 is essentially the heart of this course. We are looking at now ARIMA models. These are widely used models for time series analysis. AR, of course, is autoregressive. MA is moving average. The I is integrated. That allows you to do the differencing part. Make sure you're very, very, very familiar with the notation that we use with these models. How can I actually write out the model? There's different ways. So, for example, we can use what's called the AR operator to write a model out like this, rather than using 1 minus phi 1b minus phi 2b squared minus, we'll just make an AR2 part there. And we can see how that the autoregressive operator allows us to write this a little bit quicker. Now, with these models, we also have to worry about mu and alpha. Make sure you're very comfortable with doing that. If you ever have to write out a model, make sure you know when you need to put that alpha in there. It's very important. Don't leave the alpha out by mistake. We also looked at then, well, often we like to be able to rewrite our model as an infinite order moving average model. What's one reason why? Well, because essentially, that's what that is there. And that allows us in a direct connection to get an autocovariance function. Or you can keep on going through some of the derivations yourself, excuse me, to derive an autocovariance function, then the autocorrelation function as well, by writing everything out in terms of an infinite order moving average. Make sure you can actually do it. You can actually do it on the tests. If I gave you AR1, could you actually go through the derivation? Now, we also have a function that's available to us in R that helps simplify some of this. We have this ARMA to MA. One thing to think about, too, is that, let's say I have you derive it, and you have, let's say, 5 or 10 minutes extra on time left on the tests where you can check your answers. Well, what you could do to check your answer for the derivation that you did is plug in some possible values of phi1 or phi2 or whatever you're working with there, and put it into ARMA to MA, get a numerical value out, program the actual expression that you derived into R as well, see if the values match. If they do, then most likely you got the right answer. Now, other times on a test, I've asked students, okay, take advantage of all the tools that are available to you. Here's a phi1, here's a theta 1. Write the model out as an infinite order moving average. So in that case, you could go immediately to ARMA to MA to write it out. We talked about causal models, invertible models. We've spent a lot of time focusing on how the ACF and PACF can be helpful tools to understand what's an appropriate model for time series data. So make sure you understand these characteristics that we look for. If you remember, there was a nice table that kind of summarized what should happen in terms of the tailing off to zero, the cutting off to zero. We also have a function called ARMA ACF that allows us to actually see what the true ACF would look like, for example. Make sure you're comfortable with using that function. Then lastly, we talked about estimating these models. Again, we're just focusing on maximum likelihood estimation. We use the ARIMA function to estimate the model. Make sure you understand the arguments that we've at least talked about so far in our class that are available to us in the ARIMA function. Make sure you're familiar with how to get information out in terms of you fit the model. You put it into an object, let's say called mod.fit. Can you get information out of that? So you can further examine what this model fitting is giving you. Make sure you can properly write out an estimated model. And again, just as emphasis, don't forget about alpha hat if it's needed. This last note here, I say example of tailing off plots. That's what I showed you earlier. Okay. So, time's about 10:30. That's all I have to say specifically about the tests. Do you have questions? Now, on my tests, and perhaps you can, if you've had, again, a test for me, hopefully you agree that this is true. If you haven't had a test for me, you can confirm it. It is true with those students who have. On my tests, I don't like to give surprises. I make the tests doable. I want everyone to get A's on these tests. I don't, let's say, make a test so that I expect students to get a 50%, and then I scale them so that everyone gets in the 80s or 90s. I don't write tests like that. I've never scaled the tests in my 30 years of teaching. I tried to make, I think I do make them doable. Yes. Obviously, the scratch paper that you bring into the test, well, yeah, thank you for bringing that up. You can bring scratch paper into the test, but obviously make sure there's no writing on it. Okay? And ideally, I'd like to only see one sheet of paper out at a time. I'm sorry to be that picky, but again, as I've done this for 30 years, unfortunately, I have seen times where students have cheated on tests. Do note that during the test, again, you'll be using these computers. Please make sure your eyes are on your own computer. Don't be like looking ahead of you, your neighbor's computer. Also, during the test, I will be camped out in the back of the room. So during the test, you can come back there to ask me questions that may occur. But also another reason why I do that is because I kind of want to see what's on your computer screen as well, just to make sure that you're not looking at something that you're not supposed to. It's been rare, but there have been occasions where even though I say, no, you can't look at my notes. Again, here, you cannot look at my notes on the test. And a student will have all my notes opened up on his computer. It's happened before. I said, no, you can't do that. It is a closed book, closed note test. I've never had a student, though, or at least I've seen, open up one of my videos and start watching the video during the test. Perhaps because they're worried that maybe they might accidentally forget to turn off the sound. That would be really bad during the test. All of a sudden, you hear my voice saying, okay, here's an ARIMA model. But anyway, are there other questions? No. Thank you for asking that. I want you to rely on what's on the website itself. And the reason being is because, not saying that you would do this, but you could bring in something that you shouldn't have. You could easily type notes into those R programs. Unfortunately, it's kind of like the old-fashioned trick. Perhaps this is too old-fashioned. Of when people would actually bring some graphing calculators into a test. For a stat course, and they would type in a whole bunch of notes onto those graphics calculators and use that to help them take the test. So, other questions?
I'm just confused with the downloading of the R program because in your website it puts in a new tab in the browser. So is that what it means?
Thank you. Thank you for bringing that up. So what I recommend that you do, so I'm in Edge here, but you could do the same thing in other web browsers. Just come here, mouse over, right-click, Save Link As. And that will download the program to your computer that you can open up. So if I do that, it asks me where do I want to download it. Typically, like there's a downloads computer folder on your computer, and it will actually put the formal program there. Alternatively, what some students will do is that they'll just click on it, and obviously it opens up in the web browser. This is just an ASCII text file. You can copy and paste that into RStudio or whatever.
This would be fine.
Yeah. Yeah. Other questions? Okay. Excuse me. Again, before you leave this room, I do recommend that you log on to these computers just to make sure you can, make sure you understand where everything is, Make sure you're comfortable with what RStudio gives you. Of course, you could just use plain old R. There is an editor in that as well. TIN is not on these computers. It's not worth the fight for me to get them on these computers. I have tried before, and it can be difficult. Now, if you two things before I go to what's next. First, if you have any questions before our tests, please feel free to post them to the discussion board. I'm happy to reply to them before our test. Second, I'm okay with starting the test even a little bit before 9 a.m., but I'm not going to do it unless all 12 students are here. So let's say at 8:55, all 12 students are here. I'll start it. I'll give it to you earlier, just so you have more time. Okay? Don't all come here at 8 a.m. expecting to start at 8 a.m. But typically in the past, I will go at most, let's say, 15 minutes past the normal time for the test, and this, because of this unique situation, I cannot. But if everyone is here early, I will say, okay, the test is available to you. Okay? Any questions about that? Okay. So what's next in our class? Obviously, I'll be available for questions after class. You do have that quiz that's due, like our normal Tuesday quiz. Don't forget to do that. On Thursday, I will be in this room shortly after 8 o'clock. I will have my normal office hours, you could say, at 8:30. The tests, at the latest, will be made available at 9 a.m. Then next Tuesday, I will have my normal office hours. We'll have our regular class. This class will talk about the second part of the forecasting part of our notes. And so, make sure you do take the time to go over it. The amount of material for next Tuesday is less than what we normally have, just like it was for this Tuesday. And the reason being is because of the test. We will also discuss the grading of test number 1 as well. Looking further ahead, project number 3 is due on Thursday, April 4th. Sorry again that I kind of messed up when I was thinking when it was due. Test number 2, so that we can really look farther ahead, is April 25th. And the reason why I want to put that out there is because, obviously we haven't had a test yet. The second test does come more quickly than the first test did. And that's just the nature of the material. That's why I organize it like that. Okay, any last questions? Okay, well, good luck with your studying, and I will see you on Thursday.